Well, hello, physical geology students, and welcome back this week. We're going to talk about igneous rocks. Last week we talked about volcanoes, so this week we talk about the things that volcanoes make, like this mountain behind me, behind us on this screen, Mount Kilauea, erupting its fountain of lava here, which will eventually cool into a basalt. But how does that happen? What makes that happen? So let's remind ourselves there are three types of plate boundaries: transform, convergent, and divergent. Divergent boundaries, of course, where we have a very shallow geothermal gradient, where the heat is very close, in other words, to the surface. We get a particular kind of igneous set of igneous rocks that are very mafic in composition because of the mantle material that's upwelling. Conversely, at convergent boundaries, whether it's oceanic or continental oceanic, you'll get different suites of rocks with these as well. They tend to be more felsic in composition because of the whole process of magma differentiation as a magma cools, or for that matter, as it mixes, or whatever the case may be. You have a pretty complex series of geological processes going on beneath within the lithosphere at places where you have partial melting in the upper mantle above the subducting slabs. But let's talk more about that. So specifically at divergent boundaries, of course, you have an upwelling of hot asthenospheric rock moving upward, being pushed upward by a mantle plume, and that rock tends to be very rich in iron and magnesium, very mafic in composition, and so hence this is what's actually producing new ocean floor. And the new ocean floor is going to be composed primarily of basalts and gabbros, and you already know that. If we go back to our little trip through the Moho back in our first virtual field experience, we talked about basalt and gabbro and oceanic lithosphere. So you're already familiar with this. You've heard this before. It's nothing new. If we look at subduction zones, though, it's a little more complex. So in this case, we have a low-angle subduction situation where an andesitic volcanic arc is developing further inland. This is closer to our Rocky Mountain situation, although the Farallon plate, which is the subducting plate that's connected to the Pacific, is actually even an even lower angle than this. But regardless, this is typical of a continental oceanic subduction zone. You're going to get a lot of metamorphosed basalt through here. You're going to be bringing water down and then hydrating the upper mantle here, which is going to lower the melting point and allow more buoyant liquid rock to move upward. And as it does, it's going to assimilate some of the country rock, which is going to make it even more felsic in composition. So that by the time it gets up here, the magma is much thicker. It's got a much higher volatile content, and it's going to be a lot more explosive. So any volcanism along a spreading center is not terribly explosive. It's mostly just lava flows and so forth. But over here, these tend to get very violent. Likewise, in this situation, where we have a typical high-angle subduction zone, where you have a variety of magmas being produced. So here we have water from the subducting plate, lowering the melting point in the mantle itself, where the rock is pretty much ultramafic. So what happens, of course, is you're melting the ultramafic rock, and it's important to remember, we haven't talked about this yet, but the first minerals, we'll do that in a second. The first minerals to crystallize or to melt rather in the upper mantle are going to be the silica-rich minerals. And so any molten rock you produce in the upper mantle is already going to be enriched in silica at this environment. So as it does that, it assimilates more and more of the country rock, and eventually keeps increasing. So it becomes from ultramafic, it'll become mafic, and from mafic to intermediate, and from intermediate to felsic. So by the time it gets up here, it's got a very high silica content. All right, so of course, these are all different kinds of intrusive features, and these features form as a result of those upwelling magma, diapirs and batholiths and so forth. So you see, these are all different kinds of intrusive features, but they come in a whole variety of forms. Everything from the giant batholiths, like a Yosemite Park half dome sort of situation, to various kinds of dikes, which are just discordant features that cut across bedding planes and act as magma conduits. You can see how the geometry behaves. Sills, which are horizontal and concordant. In other words, they don't necessarily break through beds. And then, of course, laccoliths or lava domes, which are flat on the bottom and domed upward. These, if they're shallow, will tend to actually produce a bulging effect. Then you have volcanic necks and so forth. But these are all the different kinds of things. Most of these are feeder materials from the main batholith. And of course, as magma makes its way up, it first makes its way through cracks. And this is eventually the process of magma moving into bedding planes and moving through cracks in the rock, and then assimilating or breaking apart that rock is actually called stoping. But these cracks serve as the initial conduits, and then you get dikes and sills from there. And then, of course, as it moves up and as it incorporates part of the rock, it's going to start. It moves in there. Here's a pluton that's been solidified in place, other in place plutons, and so forth. So you're producing more in place plutons eventually, and these eventually cool. And then when they erode away, you're left with particularly interesting landscape features, such as Yosemite's Half Dome, which is what this is trying to get at here. All right, or things like Ship Rock, New Mexico, where you have a sheet dike leading straight away from what used to be a volcano. So it's a volcanic neck here, this giant, beautiful giant rock. One of these days I'll get out there and check it out. But anyway, so these are intrusive features and some of the features they produced on the surface. You'll have already looked at Devil's Tower and the Black Hills, which is a dome feature. Where you've already seen some of these things, or those lamprifier dikes at Great Falls, Virginia. Those are another example of intrusive features. Again, last week's virtual field experiences. All right, well, let's talk about how magma is generated, and then how we produce rocks from that magma. So first of all, just a review of the geothermal gradient again. As you go deeper into the Earth, it gets hotter, but unless the geotherm crosses over the solidus, you don't get melting of rock. You can get metamorphism, which we'll come back to in a couple of weeks, but you're not going to get actual melting of rock unless you have a really high ramping up of temperature at a shallow depth, like such as a mid-ocean ridge, or a hotspot situation where you get really hot magma material or mantle material at a shallower depth, or if you add water to the rock, in which case you hydrate it and you end up with partially melted, I should say, upper mantle rock above the subducting plate. So there's several ways of doing this. When you're doing it at a spreading center, it's decompression. You're taking the pressure off of the rock below, and it actually causes it to melt. And that's commonly what happens at spreading centers. There's also flux melting. It's subduction zones because you're adding water or adding other volatiles. You're adding it's a form of flux, and when you add that, it changes the melting point of the rock, and it actually causes it to melt at a lower temperature. But you can also just add more heat. So if you add more heat, eventually you're going to melt that rock. Even if it's under a lot of pressure, if you can add enough heat, you're still going to melt it. Well, these are the three main ways of melting. We've already talked about them, but these are their technical terms: decompression melting, flux melting, and heat-induced melting. So again, as we go deeper into the Earth, you see the geotherm does towards the inner core. It eventually levels out in terms of the temperature at very high temperatures. The outer core is a little cooler, and then the mantle is a little cooler yet. Really, the temperatures ramp up to about 410 kilometers deep, and then by the time you're down to the upper mantle, you're at 1900 Kelvin, which is certainly enough to melt quartzes and things like that. So how do we change the chemistry of magma? So it's okay. So you can melt a rock, but magmas don't necessarily just stay the one chemistry. Of course, there's a whole variety of chemistries they can become. So you can either partially melt it, which is what you're doing above a subduction zone. That subducting slab, of course, again, is bringing water down with it and partially melts the upper mantle. As that happens, of course, the rocks melt in a particular, or the minerals in the crystals in the rocks melt in a particular order based on their mineralogy. So we'll get to this more in a second, but the quartz will melt first, followed by muscovite and potassium feldspar and so forth. And of course, when you do that, you actually enrich the magma in silica. Now you can actually, this is according to Bowen's reaction series. Again, we'll get to that in a second. Magma differentiation, there's two ways of differentiating a magma. One is through assimilation. So this is where you add country rock to the magma. As it moves up buoyantly through the lithosphere, it will begin to incorporate xenoliths, which it can melt. Xenoliths meaning foreign rocks. that it can melt. Sometimes they melt, sometimes they don't. If it stays solid, if it never melts, it's just called xenolith. But if it incorporates it and melts it completely, then you're adding that chemistry now to the mix. You can also fractionate the magma, and this is a way of depleting it. So here you can add materials to it, and here you're taking materials away. As the magma cools, certain minerals will crystallize out first. In this case, the mafic minerals will crystallize out first, the olivines and the calcium feldspars. And finally, you can mix magma chambers. So let's say you have a magma chamber hanging out, doing its thing, and then another magma of a different chemistry intrudes. Now they may not be able to mix, but they can miss. They're missable, perhaps. But then they are able to commingle, and their chemistries will eventually change because of that mixing. So, of course, this is kind of how you might want to visualize these things. These aren't necessarily big holes in the ground like you see here. It's usually not quite that dramatic. But as you're moving along, the magma is rising, and as it's rising, it's typically becoming more and more felsic as you're melting more and more quartz-rich rock into the magma until it becomes very explosive up here. And of course, the moho itself, the boundary between the crust and the upper mantle, does play a role in all of this. Eventually, the upwelling mantle will pool underneath at the base at this boundary until it is able to assimilate enough country rock to be able to become buoyant again and move its way upward. All right, so of course, this is an example of fractionation. So where the original magma begins to crystallize out pyroxene, followed by pyroxenes and amphiboles and so on until you've crystallized out almost everything but the SiO2, leaving nothing but quartz left to crystallize. Changing the composition of the magma. Now, when you do crystallize magma, you're freezing it, is what you're doing. You're taking a liquid and making it into a solid. It's freezing. It just doesn't seem like it's frozen, right? Because when you think of frozen, you think of cold. Well, for magma, a rock is cold. So perspective is everything, right? So when you're freezing a magma or lava, you're going to produce a rock with a particular texture and composition. And we classify these rocks based on texture and composition primarily. These are physical classifications. They have a certain chemical set of chemical connotations with them as well. So we can classify minerals. Yes, we can do that with minerals too, but we can classify igneous rocks based on their physical texture and composition, and also based on their chemical composition. But most of the time, we haven't done a chemical analysis on the rock. If we're just in our lab, we're doing our thing. We're not going to be doing chemical analyses on the rocks. And so the only thing we can do is give them a physical classification. Is it a granite? Is it a gabbro? And so forth. This is actually a little out of place here. So this is an example of fractionation. And then this is an example of assimilation. And this is an example of magma mixing. So you can pause here and study these. That's what I'd recommend you do. But then go back and start teaching yourself about igneous rocks again. All right. The chemical classification of igneous rocks consists of, there's two systems or two schemes used. One is to look at the sodium and potassium within the rock. Again, you have to do this using various lab methodologies, and graphing that against the silica composition here on the x-axis. This is what's called a TAS diagram, total alkali silica. And so it allows you, once you know the silica composition, silica percentage, and then the combined percentage of these two species, you're able to then plot it somewhere around here. So your basic magmas, this is mostly for volcanic rocks, or extrusive rocks, the rocks that come out of, that are on the surface. So, basalts and andesites and rhyolites and so forth. So for plutonic rocks or intrusive rocks, we use a QAPF classification scheme where we're looking at quartz, alkali feldspars, plagioclase feldspars, and then phoidolites or phoid rocks that have very low silica but are much like feldspars. So these are obviously opposing. You're not going to have a lot of quartz and a lot of phoidolite type minerals in your rocks because they don't exist together. Typically, that's the same of potassium feldspar and plagioclase. So because of those chemical realities, we're able to, if you can get some percentages on two things, then you can assume the percentage of the thirds, which is kind of nice. This is what we call a double ternary diagram. And so, 100% alkali feldspar is down here. 100% quartz is up here. We can actually call that a quartzolite. And then 100% plagioclase feldspar will be over here. Likewise, if it doesn't actually have much quartz or no quartz in it, it might be a phoidolite. These are more rare down here, but so most of your plutonic rocks or intrusive rocks are going to plot up here. But you need to remember it's 3 points. So your percentage in terms of the 100% bulk composition of the rock, you're going to have 3 numbers here, and you have to have 3 numbers to be able to plot it on here. But that's how we do it chemically. Physically, this is another version of it, and I'll pass out a version of this you have in class. So physically, we look at the texture and composition, and we're kind of judging it based on our assessment of, on some level, the bulk color of the rock. If it's very green, like this, we know it tends to be lower in silica, like olivines and so forth. And there'll be komatiites and peridotite. Komatiite is a fossil rock. It no longer exists. No longer gets erupted, I should say. It's not really a great way of putting it, but peridotite is just pure mantle rock. It's plutonic, large, coarse crystalline mantle rock. All the way up to felsic, which is lighter in color, and a lot of pink and white minerals in it. And then, of course, there's the different textures, from phaneritic, and there's another one up here called pegmatitic, on down to pyroclastic. And once you know whether it's porphyritic and intermediate, then you can call it an andesite porphyry or a porphyritic andesite. You can give it a name. And that's what we'll be doing in lab, is primarily doing the physical classification of igneous rocks. Although I'll bring some trachytes and phonolites in from Kenya for you to take a look at. This is Bowen's reaction series. We have alluded to it several times here. But this is the high temperature end. This is the low temperature end. This is the ultramafic end. This is the felsic end. So if I start to melt a rock, these are the minerals that are going to start melting first. These are the ones that are going to, if they're in that rock, are going to melt last. Most rocks don't contain both quartz and olivine. That's a very unusual situation. If you have both quartz and olivine, you'd have, in fact, it's almost impossible because you have this intermediate composition that gets in the way. So quartz and olivine just doesn't exist together. But you could have a oligoclase, and have an olivine and so forth. So it's entirely possible to have certain intermediate and mafic compositions together. But the bottom line is this is the order of cooling from the top down and the order of melting from the bottom up. And that's just trying to get over here with it. Well, actually, yeah, this is looking at increasing silica on down and increasing iron, magnesium, calcium on up. All right. So what do these look like? So ultramafic rocks tend to be very green because they have so much olivine in them. So if you look, this is the one that no longer exists. So once upon a time, billions of years ago, there were komatiite lava flows. There are no longer mantle lava flows coming out of the earth. So if you can find a komatiite, I think the only place you can get them is in South Africa. They're actually named for a type locality in that area. It's not the only place you can get them, but it's one of the key places. And then peridotite, and I'll have some samples of peridotite for you to look at. But there are 4 varieties of peridotite depending on the mineral makeup of the rock. But we'll just call it peridotite is what we'll do. Then there's mafic rocks, such as this vesicular basalt. You see it's very vesicular because of the vesicles or the holes in it. And this gabbro, which has larger crystals in it. But they're a little hard to see, but if you look closely, you can see the bigger crystals. Of course, this is a 2 centimeters scale. They aren't massive. They're just big enough to be visual. So, phaneritic, where's the boundary between coarse grain and fine grain, or phaneritic and aphanitic? That's a great question, and it's a bit of an art when it comes to identifying these. So intermediate rocks, if we look at the ground mass here, this is an andesite, this is a diorite. You can see the big crystals here, the white quartzes and feldspars and the black pyroxenes. And then over here, or amphiboles perhaps. And then over here you have larger phenocrysts, larger crystals, and then a much finer ground mass of feldspar ground mass. But it's much finer. So this is the extrusive version. This is the intrusive version. Intrusive gave it more time to cool, hence the bigger crystals. Extrusive, it cooled rapidly and has smaller crystals. Felsic rocks, again, likewise, you can see the connection here between these two. This is a rhyolite, and this erupted out of a volcano volcanically, so extrusively, and then this is a granite, so it cooled within the ground, has larger crystals. And then there's one other lava you should be aware of. There's only one volcano on the planet that erupts this kind of lava, and I wish I could say that was me there. I've been to Kenya, and I was just over the border from Oldonyo Lengai, Tanzania, and I didn't make it down there, but you can see it's very interesting, a very interesting rock, carbonatites. So it's a carbonate, actually. It's not your typical marine carbonate, but it's a carbonate. So you can see there's very low temperature volcanism as well. This is in East Africa, and you can see the very interesting, very dark colored and light colored lava that comes out of this eruption. One day I'd like to get back there and check it out. And then other textures. So again, vesicular, this is scoria, this is pumice, and then we've got other pyroclastic rocks, the glassy obsidian, and then tuff, which is basically a welded ash deposit. And then we have pegmatites, which have really large crystals, so really coarse grain, and then porphyritic, where we have a fine-grained matrix that cooled rapidly, surrounding bigger phenocrysts that had. There's two cooling periods to this rock. It cooled slowly at first, and then was erupted, and cooled rapidly the rest of the way. So porphyritic. And that brings us to the end of this. So in lab, we'll talk about some of these rocks, identify them, and then go from there. So look forward to seeing you there.